starting. It says we are live. I will wait for the actual news from the chat room that we are actually live before I actually start rolling here. Oh, there it goes. Identity 4 says that we are live. So hi, everybody. We're going to get going here. Ready for a show? Ready for a show? Starting in 3, 2. This is TWIS. This Week in Science, episode number 685, recorded on Wednesday, August 29th, 2000. I cannot say the date today. What is wrong with me? Oh my goodness. I don't think I've had to re-record one of these in about 685 episodes. I have a menagerie and a mumbling mouth. Beginning again in 3, 2. This is TWIS. This Week in Science, episode number 685, recorded on Wednesday, August 29th, 2018. Double slits and quantum weirdness. Hey everyone, I am Dr. Kiki, and today we will fill your heads with surfers, double slits, and motherhood. But first...
Disclaimer, disclaimer, disclaimer. Hey, you know that cool post you saw today? You know the one. That one that was funny. No, maybe it was scary. No, it was thought-provoking. No, it was the one that proved a point you already believed in. Well, anyway, even though Aunt Helen or Cousin Joe or that cool girl Stacy, or even maybe it was your annoying but constantly present on social media coworker Karen, nobody cares about your cat's inner monologue, Karen. Well, even though they shared it this morning, there's something you need to do before you hit share. Please, 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 for the love of Sagan, check your facts first. Do a quick Google, look for dissenting articles, or at the very least, maybe click on the link. Because that killer spider that killed 5 people and they're all dead, it turns out it was a woodlouse spider and it never killed anyone ever. So pull up a chair and a set of headphones, grab your thinking cap, and join us for some reasoned discourse meant for more than shares and likes, though we wouldn't say no to some, here on This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening, what's happening, what's happening this week in science. What's happening, what's happening, what's happening this week in science.
Good science to you, Kiki.
And good science to you too, Blair. We are down a Justin this evening. He's moving, and I don't think he doesn't have a couch, or he hasn't been able to get he hasn't gotten comfortable in his new crater on the moon, I think is really where he's sitting at this point. But so we will miss him this week, unfortunately. But we have a great show lined up for everyone out there. Thank you for joining us once again for another episode of This Week in Science. We have so much fun science news lined up for you. I brought stories. What did I bring stories about? I have stories about surfing particles, less nutritious air, and we will have an interview about quantum science and famous experiments. You may know which one we're referring to, but we'll get to that in a bit. Blair, what did you bring this evening?
Oh my gosh. I brought some fishy healthcare. I brought naked mole rat poop. I brought some turtle fossils, and I brought some whiny teenagers.
Whiny? Why?
Oh my God, I can't even.
Oh, I don't have a teenager in the house yet. I just have a 7-year-old, and he's wonderful. No whining whatsoever.
Uh-huh.
Uh-huh. But before we jump into this show, I do want to remind everyone that you can, if you have not done already, subscribe to the This Week in Science podcast on iTunes, in the Google Play podcast portal, Stitcher, Spreaker, TuneIn, YouTube. You can find us there. Look for This Week in Science. You can simply go to twist.org and find all this stuff there if you want the easy way to it. But please check it out if you have not previously. But now it is time for our guest of honor, our interview for the evening. I would love to introduce our guest, Anil Ananthaswamy. He is an award-winning journalist and former staff writer and deputy news editor for New Scientist magazine. He has been a guest editor for the science writing program at the University of California, Santa Cruz, and he organizes and teaches an annual science journalism workshop in India. He is a freelance feature editor for PNAS, the Proceedings of the National Academy of Sciences Front Matter. And he also contributes regularly to many, many outlets that publish quality science journalism. The Edge of Physics and The Man Who Wasn't There were his first two books, and now he returns with another, Through Two Doors at Once. And this is the new book that we are looking forward to speaking with him about this evening. A book about the elegant double slit experiment and its influence on our understanding of the quantum world, a journey through the history of these experiments. And Nil, thank you so much for joining us tonight on the show.
Well, thank you very much, Kiki. It's a pleasure to be here.
Yeah, it's wonderful. I mean, before the show, you brought up it's been about 10 years since the last time you and I spoke. You weren't on This Week in Science. You were on a show I was doing back then called Dr. Kiki's Science Hour. I think that was it was about 2010. So that we spoke about the edge of physics and had some wonderful conversations then. What have you been doing for the last almost decade?
I continued being a journalist, so writing for New Scientist and, as you said, a bunch of other outlets, but mainly for New Scientist. And then I worked on my second book, which was called Man Who Wasn't There, which was about the neuroscience of the sense of self. And that took a good 5 years out of those 8 since I haven't seen you. Yeah. And then the last 3 years I've spent writing this new one, Through Two Doors at Once.
How did you come to write about this topic? The double slit experiment, it's a famous physics experiment. Even people who are not physicists have heard of the double slit experiment. Many people have written about it. There are short films about it, long films on it. What brought you to talk about it in this book?
I think, you're absolutely right. The experiment has a certain position in science, in popular science, but also in popular culture. I realized that there was a story here when I would do a lot of journalistic pieces on quantum mechanics, and when there were counterintuitive things about the quantum world that I was asking the scientists to explain to me, they would invariably say something like, "Oh, it's all in the math." And then if I would press them further, then some of them would resort to using an experiment to explain what they meant. And more often than not, the experiment they would choose was the double slit experiment or some variation of it. And I think that was when the light bulb went off. Like I said, okay, this experiment is not just a curiosity. There is something very fundamental that's going on when one does this experiment that could potentially be used to understand pretty much all of quantum mechanics. Or not understand as much as understand all the conceptual issues that come up when you think about the quantum world. There are things that are still unexplained, but the beauty of this experiment is that it shows us what those issues are.
I think that's just I hadn't realized it. I mean, when I think of quantum mechanics, and the double slit experiment, I really just think of it in terms of light, and the Keanu Reeves quotations of "it's a particle and a wave, man," and that's just kind of where I leave it. But for you to take it even further and show its influence in the entire field, really, and all all the great minds who have worked on variations of it, and how basically it's like that's just iteration, step-by-step iteration and addition of new ideas on top of the ideas from which it started. How long ago?
The first double slit experiment was done in the early 1800s, 1802, 1803, by an English physicist, Thomas Young. And he did it just to show that light is wave-like in nature. Until then, we used to think that light is made of particles, which is a theory that was put forth by Isaac Newton, no less than Isaac Newton. And he, his theory, the corpuscular theory of light, was that light is made of corpuscles or particles. And when Thomas Young did this experiment, he realized that no, light actually behaves like a wave. And it's an extremely simple experiment, at least the way that Thomas Young did it. And even now when we do it, conceptually, it's so simple that it boggles your mind that it could be hiding anything important. You essentially take an opaque screen, cut two openings in it, two slits, and then shine light at the two slits. So light has basically two ways to go through the opaque screen, either through the right slit or the left slit. And on the other side of the opaque screen is some photographic plate or some screen where you're watching what happens. And your intuition tells you that the light should just go through one opening or the other opening and then create two strips of light on the other side. And what Young found was that it doesn't do that. You get these bands of alternating bands of light and dark. So in the center is a bright band, and then next to it are two dark bands, and then light bands and dark bands. And this is a very characteristic thing of how waves behave. So what Young was seeing is something called an interference pattern. So you can easily understand this if you think about a break wall that is keeping out the ocean waves at the beach. And there might be two openings in the break wall, and the ocean wave comes and hits that break wall. And then from each opening in the break wall, new sets of waves start coming out towards the beach. And as they spread, eventually they will interfere. So where the crests of one wave line up with the crests of the other wave, you get constructive interference. The water height is more. And when the crests of one set of waves lines up with the troughs of the other set of waves, you get destructive interference. The water level is low. So in the context of light, it just becomes light and dark. And so that was the first demonstration that light is wave-like in nature. And this was the early 1800s.
And we're still really trying to figure out, have we really explained that yet? Or are we still in the process of figuring out how that's possible?
Well, the stuff that Thomas Young did, yes, we can explain that, because that is just done using a lot of light, and it's easy to treat light as a wave when you're taking a flashlight and shining it at these two slits. But all of this stuff changed when quantum mechanics came along. So when quantum mechanics or quantum physics was born in the early 1900s, Einstein was the first person to show that actually light is made of particles, that all energy comes in quanta, or tiny indivisible units. So if you have red light, for instance, red light is actually made of tiny quanta of red light. These are called photons, or photons of red light. And you cannot divide these photons into anything smaller than that particular unit of energy. So light is actually made of particles.
Right.
And then when you do this double slit experiment with single photons, one photon at a time, things get really, really messy in terms of trying to make sense of what's going on. So now, if you imagine firing one photon at a time at the two slits, you're creating a single particle of red light, or any frequency of light, but let's stick with red light. You're firing individual photons. It's as if you're sending particles of sand at the two slits. And on the other side is a photographic plate that is registering where the photon goes and hits the plate. And again, your intuition now is clearly telling you, look, I'm creating single particles. It has to go through either the left slit or the right slit. And then on the photographic plate, these individual particles should bunch up right behind the two open slits. Of course, this is quantum mechanics, so that doesn't happen.
And nothing occurs according to intuition, right?
No, so exactly. So our intuition fails us dramatically here, because what happens is that if you did this with thousands and thousands of photons, over time, as these photons keep hitting the photographic plate on the behind the opaque screen, you realize that the photons are going randomly to different locations. They're not going right, you know, to the location right behind the two open slits. In the beginning, it seems like they're just randomly going all over the place. But over time, as these photons pile up, you get the same interference pattern back. So the photons bunch up in areas which can be called regions of constructive interference, and they don't go to areas which can be called regions of destructive interference. But here's the problem. We're not sending a wave. We are sending a single particle, right? And we know this particle, quantum physics tells us that this particle cannot be divided any further. So it's not like the photon is breaking up and then going through the two slits. It's not. It can't break up. So what is interfering? It's not even the case that the first photon is interfering with the second one or the 10th one or the 100th one. You can send them 10 seconds apart, and this will still happen. So this is the question. You're creating single particles, you're detecting single particles, and yet you see an interference pattern. The question is, what is going through both slits? And in some sense, this is at the heart of some of the basic questions in quantum mechanics.
Yeah, how can it be in almost all places at once? How can it be this wave that would be passing through both slits when it's supposed to be acting like a particle? And then the question that we really get to at this point with many of these experiments is the detector and that act of consciousness, right? Is it our conscious detection? When did people start really thinking about the idea of consciousness, or at least the fact that we are detecting?
So I think to understand that, we probably have to step back a little bit to ask questions about what is it that is going through both slits. So mathematically, we know what's going through both slits. What goes through both slits is something called a wave function. It's just a representation of the state of the photon. So the photon is a quantum particle. It has a state that is captured by this thing called a wave function. And this wave function spreads. Mathematically speaking, it spreads. It behaves exactly like a wave, and it hits the two slits. And just like water waves on the other side, this wave function, breaks up, goes through both slits, interferes on the other side. And then you have regions where the wave function has constructively interfered and regions where it has destructively interfered. Except that this wave function is a mathematical abstraction. It's not, we don't know what on earth it is. And now if you want to try and find where the photon is, the wave function will only tell you the probability of where you might find the photon when you do the measurement. The measurement in this case being the interaction of the wave function with the photographic plate. So if you were to mathematically ask questions of the wave function, it'll tell you, oh, the photon is very likely to be found in these places where mathematics is telling you that there's constructive interference, and very unlikely to be found in places where there was destructive interference. But there are many, many places where there is a non-zero probability for the photon to be found. And it's only upon measurement, it's only when it is observed, it's only when the wave function is observed, so to say, does the photon actually appear in one of these places. And you can't tell for any single photon which place exactly it'll end up in. That's completely random. But the wave function has given you probabilities. So if you did this over and over again with 100,000 photons, those probabilities will be borne out. So many photons will go here, so many will go there, so many will go there, etc. Right? So this becomes the issue. Before the measurement, before the wave function interacted with the photographic plate, the photon was likely to be found in many, many places. But the moment the measurement happens, the wave function, which is spread out at that point, collapses. It collapses and the photon materializes in one place. So mathematically, standard quantum mechanics says that it is the act of measurement that collapses the wave function. And that's where the observer comes in. So the and some people have taken this to mean that observation actually requires human consciousness. Actually, standard quantum mechanics doesn't make any claims about what is an observation. In fact, that is the central problem with standard quantum mechanics. There's a name for it. It's called the measurement problem, because quantum mechanics actually does not define what a measurement is. It does not tell you how big the measurement apparatus should be. Is it, size of a little, it could be any tabletop thing. Does it require humans around? Can a cat observe that and still see the interference pattern? It doesn't make any claims. So it
if
leaves
you
it
have
open.
if you have a cat in Schrodinger's box, does it observe the collapse of the wave,
issue.
function?
Yeah, and Schrodinger's cat. I'm glad you brought up Schrodinger's cat, because Schrodinger's cat is essentially Erwin Schrödinger making up a thought experiment, pointing out that it is so bizarre to have a theory which doesn't define what a measurement is, and yet says that the act of measurement should collapse the wave function. So that's why you end up in a situation where you find the cat being both dead or alive until there's a measurement. And some people have taken that to mean that human consciousness is needed for collapsing the wave function. But we have to be very clear. There is nothing in standard quantum mechanics that says anything about human consciousness. Those are just ways in which people have taken this and run with it. And but the experiment is beautiful because it's already showing you a few basic things about what's weird about the quantum world, right? One is the fact that it's non-deterministic. You can't tell where the photon will go. So if you did this in the classical world, if you took a baseball and threw it across the field, if you were an accurate thrower, you would be able to predict exactly where it'll go, plus or minus this way or that way a little bit. But your equations of motion, Newton's equations of motion, can tell you exactly where the baseball will go. You can't do that with quantum mechanics. You fire a photon at the two slits, it'll end up in any one of the locations where it has a non-zero probability of being found upon measurement. So which means that you can't chart a single trajectory of the photon through the double slit. And in fact, in standard quantum mechanics, there is no way to talk about the trajectory of the photon. So people have taken to saying that means that reality, which in this case is the photon, reality doesn't exist until you do the measurement. So there are interpretations of this mathematics which suggest that quantum mechanics is anti-realist or non-realist, which means that objective reality doesn't exist until there is an observation. But of course, not everyone accepts that, but that is one of the implications of the theory.
Or it exists. I mean, you can take the philosophy even further. It exists because we are here to observe it.
yeah. I mean, that's one interpretation. Exactly.
Yeah.
But there have been many well-known physicists who have disagreed with that, including starting with Einstein and Schrödinger. Both of them, Einstein especially, was of the opinion that reality exists independent of any of us. That and our theories are meant to discover what the reality is. Whereas the Copenhagen interpretation at its extreme of quantum mechanics basically say, no, the act of observation creates reality. And Schrödinger didn't like that. There were many people. There was John Bell in the 1960s. In fact, I think he wrote a lovely paper in 1990 called Against Measurement, where he said, so did the wave function wait till there were people with PhDs for it to collapse? So it's very unclear. There is nothing in the physics of quantum mechanics which tells you what collapse is. It just postulates this thing called a collapse.
Right.
And so a lot of the other interpretations that have come up of quantum mechanics are basically there to deal with this so-called measurement problem, to take away the observer from the center of things.
Yeah, I love it's this is the point though where the physics and which is very underlain with the math. The math is really the thread that ties all of it together. And I think in the book you do a wonderful job of talking about the various equations and the different lines of logic that the various physicists throughout the years have gone through. But then there is this strange point where it comes to, okay, there's math and then there's the philosophy. and we can talk about the quantum weirdness.
Yes. And none of this math or philosophy would have been there if it hadn't been for this experiment and its variations. It's because this weirdness is seen in the laboratory. It's not like anyone's making this up. The math is just trying to explain the math is trying to predict the outcome of the experiment. And it does a great job of probabilistic, of predicting the outcomes in terms of the probabilities of what will happen, right? So, but the weirdness is actually there in the experiments. And it's a question of, is this mathematical framework then, while it does a great job of predicting the outcomes, the probabilities of the various outcomes, is it really telling us the nature of reality, or is it just some abstraction that we have that is just helping us make predictions about the outcomes of experiments? And maybe it has nothing actually to. So, and that debate continues. We don't have an answer yet.
Yeah, because there still is, there's still the question of, where is the equation that actually ties our reality, our macro world that is discrete, that is predictable, together with the probabilistic world of quantum weirdness, right?
And I think one should point out is that the quantum theory is an extremely successful physical theory. It is the most successful theory of physics that we have. And the classical physics, the physics that governs the macro world, kind of emerges at a limit from quantum mechanics. So quantum mechanics as a theory is fabulous. So for people who actually use it to do their work, like people working in chemical physics or any of these other areas where you need to deal with quantum mechanics, they are perfectly happy using the math to make their predictions. And in fact, the fact that we are communicating over the internet would not be possible if it weren't for quantum mechanics. So obviously it works. No one disputes the validity of the math, but what they definitely dispute vehemently so as to what it's telling us about the nature of reality, of what actually exists.
Someone in the chat room brought up an interesting question, which it makes sense looking at it, but I've never actually thought of photons and light in this way. I've always thought of photons as light, but really it's the release of energy that is the light that you see. And so someone's asking, what if the photon is light itself and it emits light too? So we see both the photon and its emitted wave. So is there a possibility that there's there's a greater connection? But I think that the real question here is where do the photon and light actually, how do they relate to each other?
Photons are light.
They are light.
Yeah. So light is electromagnetic energy.
Yes.
And a photon is the smallest unit of that electromagnetic energy. That's all it is. So
that's all it is. Yes.
Photons comprise light, and taken together, it's electromagnetic energy. Individually, it's the smallest unit of electromagnetic energy of that frequency. So whatever color of light you might be looking at.
Yeah, I was just thinking though that when we see the blue sky, we're seeing the scattering of light at various frequencies. And we're seeing the actual the transduction of vision is the photons hitting the retina in our eye.
And our retinas have been shown potentially to be sensitive to individual photons.
Yes, that trigger chemical reactions that tell our brains that it's this kind that you're seeing.
This color.
This color, yes. Yeah. The photon triggers electrons to move to create chemical changes that tell the neurons in our brain, this is what color you're seeing.
Yeah.
So in thinking about this experiment, and you mentioned, being able to communicate over the internet, and the quantum mechanics and quantum theory is very important to modern technology. What kind of things is it important to? So the double slit experiment, it's wonderful historically. It's wonderful. Maybe it'll help us describe reality at some point. But in terms of application.
So in terms of applications, actually, the mathematics of quantum mechanics is superb. I don't think there's any dispute about that. No one's going to complain. In fact, there's a very, very famous phrase usually ascribed to Richard Feynman, but I think it's David Mermin from Cornell who said it. There's some debate about that, but it's a phrase called "shut up and calculate." So the physicists have been known to say that when students constantly ask, "Oh, what does this mean?" they pretty much say, "Well, why don't you just shut up and calculate?" Because the calculations are extremely accurate, and so everything that all of modern technology rests on. For instance, the computer chip that is powering our computers, the semiconductors. We wouldn't know anything about semiconductors if we didn't understand quantum mechanics. We have to deal with single electrons. And the movement of single electrons and single atoms and things like that. So a lot of that has to do with our understanding of how the quantum world behaves, as shown by the mathematics. So there's no dispute about that, and the double slit is not going to change that. The double slit really is a way to understand the fact that there are a lot of conceptual issues about the nature of reality that are still unanswered. And so it's not for the people who are doing the calculations and using it for applied stuff. They are fine. But there's a whole bunch of people, philosophers of physics, philosophers of science, the people studying the foundations of quantum mechanics, who are unclear. And there's a reason, because remember I said earlier that there is this idea that the measurement causes collapse of the wave function and the photon turns up in one place. That's an axiom. That's a postulate. It's not derived from first principles. We don't know how to derive that from first principles. There is a very, very important rule in quantum mechanics called the Born rule, which basically says that if you have the wave function, it has a certain value. So happens that the value is a complex number, so that's another problem. We don't know what the hell it means. But the thing is, if you take the amplitude of the wave function and square it, you get the probability of finding the photon at that location. Right? But that's again a supposition. It has never been shown from first principles, and it works beautifully. It has been shown to be correct over and over again that if you take the square of the amplitude of the wave function, you get a probability. Why is it a probability? No one knows. And has it been derived from first principles like most equations in physics are? No, it hasn't been. Neither is the Schrodinger equation, the equation that governs the way the wave function evolves and changes with time and space. It's governed by this thing called the Schrodinger equation. And Erwin Schrodinger just intuited it. He just made this incredible guess as to what might be happening, and it turns out to be correct. We still don't know why. So there are a lot of basic questions about quantum mechanics that remain unanswered. And the double slit just shines a light. But you can literally go through these variations of the double slit experiment done over the last century, and get a very clear understanding of what these questions are. The answers are not yet there, but the questions become clear, which is a lot to say for one single experiment.
Yeah, and are people moving forward on further, I guess, on further experiments, refining the method even more to be able to get to those first principles?
Yes, very much so. So
Yeah.
there are alternative theories as to what might be happening at the level of the quantum. So what I was describing so far is the standard quantum mechanics and the Copenhagen interpretation. But there is something called the de Broglie-Bohm theory, which basically says that reality is both a wave and a particle. So there is actually a wave that goes through both slits, and the particle is riding on the wave, and essentially it's guided by the interference pattern that's generated by this wave. Except this wave doesn't exist in the three-dimensional space that we are familiar with.
Right.
It exists in some hyperdimensional mathematical space. So, but it's real. Right? So it's very unclear what real means in this context. And there are experiments. And so this theory predicts that these particles are going to have very specific trajectories. They are not straight trajectories. They're kind of wonky. But nonetheless, they have trajectories, which standard quantum mechanics denies. Standard quantum mechanics says the photon has no reality until observed, and hence you cannot talk about it having a trajectory. Whereas de Broglie-Bohm theory says, no, the photon is real, it exists independent of your observation, and it has a trajectory. And there have been versions of the double slit that have been done where they've tried to find out what these trajectories are. They use certain methods which are somewhat debated and controversial, but it's they have seen these trajectories. If you accept the technique they use as valid, then these trajectories are real. So yeah, I mean, at each level, they are doing these experiments, trying to maybe find other theories that might explain what's happening better. But again, none of them have been conclusively ruled in or ruled out.
I think it's amazing. That's something that has been that we're working so hard at it. It's just not part of our reality, right? It is, as we've said, it's not intuitive. It's something that has to be worked out through math and through these experiments to be able to see it.
Yeah,
we do see proofs of it places, but that for 200 years people have been working on it, and still there are still so many questions.
yeah.
Is there what do you hope that people will take with them from this book and the story that you tell of the history of this experiment?
I think first of all, the amazing talent that experimentalists have to coax nature to reveal its secrets, the things they do with a single photon. I mean, I think it's very hard for any of us to really appreciate how small a single photon is, or how little the amount of energy is. So to actually do an experiment with single photons is itself staggeringly difficult. In fact, quantum mechanics was born in the early 1900s, and even in the 1920s, it was clear that you could do these experiments with single photons, and the mathematics was showing something very weird. It took until the 1980s to actually do the experiment with single photons. It is so difficult. And so the thing that I would want the readers to take out of this is just an appreciation for how amazing this experiment is, and how much it tells us about all of the various problems that quantum physicists are encountering when they're questioning the foundations of reality, when they're trying to understand what reality is. And it's almost beautiful to see how this one single experiment lays it out for you. You just have to analyze its various iterations and variations, and all of these problems just are right there in front of you. Not the answers, the questions.
The questions, yes. And before we go, do you have any favorite stories from your researching and putting this book together? Do you have a favorite story of either the research or researchers you learned about or interviewed?
I think my most charming interviewee was Roger Penrose.
Nice.
I had to go to meet him at his office in Oxford University, and turned out that he couldn't come the day I was supposed to go. So he sends me a hand-drawn map to his house, which he had drawn 20 years ago for a housewarming party, and had been updating it ever since. And it was this strangest map. It basically said, "Great big gate, not my house. Imposing entrance, not my house. Broken entrance, my house." So, and he was just the most wonderful physicist to sit with for 2-3 hours in his garden, in this English garden, a nippy English afternoon, and have him explain his ideas. I mean, he has some very, very neat ideas about what might be going on at the level of the quantum. He may be wrong,
Yeah.
And he will be the first to admit it. But there are experiments being done to test his ideas. But it was just the enthusiasm of this researcher who's been at it for decades and still is sharp as a tack, and it was great.
That would be wonderful. I'm a bit jealous. I think he would be a wonderful person to speak with. So that sounds great. And his proper British garden.
It was, yeah.
Having a lovely chat about physics, and it sounds fabulous.
It was fabulous. That afternoon I'll always remember.
That's wonderful. Well, as I remember our past conversations, I will also remember this conversation with you. I don't want to keep you much longer, but thank you for all of your thoughts on this experiment, for writing this book, because it is, I've been reading it and I'm quite enjoying it. And I love the, bringing through it all the different physicists, the characters, some of the, their characteristics and their personalities and how the science was done. And it's a fabulous, it's a fun read. So I'm quite enjoying it. Thank you so much.
Thank you, Kiki. It's been my pleasure. Thank you.
And where can people find you if they are interested in finding out more about this book?
My website, anilananthaswamy.com. So last name, first name.com.
Wonderful. Thank you so much.
It's my pleasure.
Yes, thank you so much for joining us once again. It has been our pleasure to get to speak with you, and have a wonderful evening. I hope other people will take a look at this book and have the double slit experiment elucidated, the light brought to their eyes. Have a wonderful evening. Everyone out there, we are going to take a short break and we'll come back with more science news. We've got a bunch of news stories for you. As we said at the top of the show, there's some motherhood to come and some surfing particles coming out of CERN we need to talk about. Thanks everyone for watching. Just a few more moments. We'll be back with This Week in Science.
Can't explain things you've heard more than intuition. A line of reason shows the way to go. New conclusion. The methods of hypothesis and patience are the only things I need.
All right, so we are in our break right now. Anil, if you would like to just hang up, that's fine.
Okay.
And I will email you with links and other things later.
Okay, great. Thank you so much.
Thank
Bye,
you
Blair.
once again.
Bye.
Yeah. Have a wonderful evening. Thank you.
Bye-bye.
Bye. Bye. That's nice. Okay. And Kai really wanted to give me a hug, so Kai's going to give me a hug, and he's going to go lie down and be quiet now.
Do you want me to start then on the?
No. Well, can you do the?
Yeah,
the
I can do this.
The mid-show flow, and I'll be back in two shakes of a lamb's tail.
Absolutely.
All right. I'll mute myself. Thanks, Blair.
Yeah.
Yeah. Awesome.
Did you know that TWIS has merchandise you might enjoy? If you go to twis.org, you can get some of our swag. We have a link on our website that goes directly to our Zazzle store. If you go to twis.org and click on the Zazzle tab, then you can check out all of the stuff that we have. I'm trying to pull it up right now. We have trucker hats. We have onesies for babies. We have mouse pads. We have mugs. There's all sorts of cool stuff. We have the specifically requested TWIS polo, which is very popular. That was actually from a teacher who listens to This Week in Science and wanted something that was in his dress code for work. So we whipped this up and put it in the Zazzle store. We also have lots of stuff with the Blair's Animal Corner images from the past few years. I will be putting some new stuff up from the new calendar with the pointillism at some point, so stay tuned for that. And if there's anything that you really want on a specific item, chances are we can get that done for you through Zazzle. So if you tweet at me at Blair's Menagerie, or you send me an email, blairbaz@twis.org, I can look into getting whatever item with whatever TWIS related image on it you like up in the Zazzle store. We can make it happen. And so all of that, there's proceeds that go to our show and help us with lots of cool stuff. TWIS is supported by listeners like you, besides just ordering fun swag. You also donate and you pay for our hosting, bandwidth, contractors we need to hire, and any fun thing we want to do for our show, anything extra. So we appreciate any amount that you can give us, $2, $5, $10, maybe $100. It's your donations that make this show possible, and we couldn't do it without you. We currently accept donations 2 different ways. We have PayPal buttons all over our website. So if you go to twis.org, you click on any broadcast or any show page, most pages you'll find PayPal donation buttons. You can do single-time donations or recurring that way. Or if you want, you could join our Patreon account. So that's patreon.com/thisweekinscience. And Patreon is kind of like Kickstarter for media producers. And you pledge a donation amount and we'll get kickbacks for that donation. So for example, there are shout out levels, there are t-shirt levels, and there are levels where you actually get a signed piece of artwork from me. I actually just sent a few of those off from last year's calendar. So those coloring pages I colored in with some colored pencils, and I sent those off to some Patreon patrons. It was very fun. Whatever your preference, go to the website, listen to the most recent episode, comment on the show, and make a donation if you can. But if you know what, if you can't afford a donation, that's okay. We can always use your help to get more people listening to and watching TWIS. That's why we're here, right? Use your social networks for science and tell people to tune in to This Week in Science. If you listen to us on iTunes, you can help by posting a review of TWIS, and even better, giving thumbs up to recent reviews that you think were helpful. That way, the more recent, more relevant reviews will pop up first when people find us in iTunes. Whatever you do, buy some stuff, give us some donations, just tell people about TWIS. Maybe just grab their phone with their permission and subscribe them so that we pop up in their podcast feed. That's a fun surprise for them. Just whatever you can do, help us spread the word. Thank you for all you do. We could not do any of this without you.
Can't explain things you've heard more than intuition. A lot of reason shows the way to go. New conclusion. The methods of hypothesis and patience are the only things I need.
And we're back. You're listening to This Week in Science.
That is right. We are back, and we do have more This Week in Science. We have a bunch of science right now, actually. But first, it's time for that wonderful segment of the show. That segment of the show that is from you out there, our listeners. This weekend, what has science done for me? Lately, yes. All right. So Nathan Heavenstone writes in to say, so this is more tech, but I was a smoker for a while, and by the end of 2013, I was smoking 2.5 to 3 packs a day. That, I am sad to say, is not an exaggeration. A friend wanted to get me off of cigarettes. I had tried things like the patch, the gum, etc., but it didn't work. My friend happened to work at a vape shop and decided to try me on that. To keep this whole thing short, within a couple of months of vaping, that is by early 2014, I had dropped cigarettes entirely, and fast forward to a couple of months ago this year, and I went 100% nicotine free. Now, it's true that I still vape, but that's because for some reason, it helps curb my sweet tooth. There's no nicotine at all in what I vape. However, just vegetable glycerin and a strawberry nectarine flavoring. And also, it's probable that I'm addicted to the actual act itself, as the simple ritual of building a coil, installing it in the atomizer, and wicking it is very relaxing. And I have an anxiety disorder, so it's good to find those things that are relaxing out there. And yeah, I think the behavioral acts can be very habit forming as well. We have all sorts. I have some terrible habits that are, They're just
Yeah, and one thing that science has done in a similar vein is recognize that nicotine is bad for you. We didn't know that right away. It took some sciencing to figure that out.
Yeah, well, the nicotine itself, yes, it's a stimulant, it's addictive, that has, it's a science we have learned these things from, but we have also learned that the cigarette smoke itself contains carcinogens and other compounds that are cancer-causing, mutagenic, cancer-causing, pretty, not great stuff. Science has led us in that direction. Science led us in the direction of the technologies to create these new alternatives for smokers, like you mentioned, the gum, the patch, now the opportunity to vape. The social stuff is still, definitely up in the air, and people are. It is not completely risk-free to vape, but it is definitely different and potentially a less of a risk. And if you're trying to manage risk in your life, choose the lesser of the evils, right?
Yeah, science has helped us identify that cigarettes aren't just an appetite suppressant to keep you thin while you make your husband's supper, right?
What? I thought we were back in the 1950s again.
Yeah. No, it turns out we found out some things.
Yeah, and thank goodness we're now in the 2000 aughts, because I don't have to wear a pair of pumps and a dress while I cook dinner either.
I wouldn't last 5 minutes in that reality, let me tell you.
Oh no, there would be some heads rolling in my world, that's for sure. But anyway, Nathan, thank you for inspiring this little bit of conversation for us. Thank you for writing in with your interesting take on what science has done for you lately, because it definitely has helped you, is affecting your life in a multitude of ways. Thank you for writing in. Everyone out there, if you are interested in being a part of this segment, you can send your thoughts, your notes to Kirsten at thisweekinscience.com in the form of an email, electronic mail. It works. Or you can leave us a message on our Facebook page. That's facebook.com/thisweekinscience. Keep them coming, everyone. Let's keep filling this segment of the show with your stories. All right. Are you ready for, since we're talking about, cigarettes and vaping and all that kind of stuff, a little less nutritious air?
Uh-oh, I need both of those things, nutrients and air.
I know we do. Well, one of the things that people have been talking about for a couple of years now is, we're putting carbon dioxide into the atmosphere, greenhouse gas, it's getting hotter. But what's the upside of the carbon dioxide? Plants love it, right? So this carbon dioxide, excess carbon dioxide, is just going to help plants grow bigger, right?
Sure.
Well, it does, and there have been studies that have shown that that in fact plants do take in more carbon dioxide. Not all species of plants, though, I will say, but some species of plants do take up more oxygen. Some, not oxygen, carbon dioxide. Some of them do grow larger. This is really exciting stuff. But a new study that just came out of Harvard Chan School, published in Nature Climate Change, finds that this change in carbon dioxide is actually going to make our food less nutritious, less nutrient dense.
Is that because they're growing faster? So
for some reason, it is leading to less zinc being incorporated into the plants. It is, which could, and less iron as well. The study found that more than 1 billion women and children could lose a large amount of their dietary iron intake, putting them at risk of anemia if carbon dioxide levels end up at 550 parts per million, which is expected. I think they're expecting it to hit that somewhere around like 2000. I don't know, not that far off. 2050, something like that, is when they're expecting it to potentially hit that. But people do get most of their nutrients from, you get your nutrients from your food. And if our food is not getting the nutrients you need, where are we going to get those nutrients from? So these researchers wanted to actually figure out the global health burden of carbon dioxide related nutrient shifts in crops in 151 different countries. They created a unified set of assumptions across all nutrients and used age and sex specific food supply data sets so that they could improve their estimates of the impacts across 225 different foods. And they found that by about, the middle of the century, 2050, when concentrations are expected to reach about 550 parts per million, 1.9% of the global population, and this is based on population estimates of 2050, which is going to be 175 million people. A lot of people could become deficient in zinc, and 1.3%, 122 million people could become protein deficient, which is pretty huge. And then, as I mentioned, the women of childbearing age and children would be at risk of having their iron intake reduced. India, they found, would have the greatest burden of these deficiencies. So not every country would share the burdens equally because of how the atmosphere and the plant, different crop types.
Oh, I thought you were
work
going to say it was
together.
because of the cultural implication of so many vegetarians over there.
That could possibly be it too. Yeah.
Because no, that's what I
Yeah,
always thought it
that's
too. When I've gone
interesting. Yeah.
to donate my blood, they ask you if you're a vegetarian. And
Right.
I say, oh, I'm a pescatarian. They go, oh, okay, you're probably fine, but we have to check your iron. Everybody who doesn't eat meat on a regular basis, we have to check your iron.
Yeah. And so, yes, you have to check your iron. You're not eating meat.
I'm wondering if, the vegetarian
And if, as you
groups will
mentioned,
have,
and if the plants are growing bigger and they just have less of the nutrients in them, they're taking them in maybe at the same rate, but because they're growing bigger, faster, there are less nutrients in the plants. And if you are vegetarian, then you would be at risk of that deficiency. This is, again, published in Nature Climate Change, study entitled The Risk of Increased Atmospheric CO2 on Human Nutritional Adequacy. And this is something that the head of an alliance called the Planetary Health Alliance, it's at Harvard University Center for the Environment and Harvard Chan School. They say one thing this research illustrates is a core principle of the emerging field of planetary health. We cannot disrupt most of the biophysical conditions to which we have adapted over millions of years without unanticipated impacts on our own health and well-being. So another reason more carbon dioxide in the atmosphere isn't potentially something we are looking forward to.
We're reaching our carrying capacity. It's pretty scary.
Yeah, and I think that's something, that was a story also, I don't remember if we talked about it on this show, it was one that came out a few weeks ago about, the estimate of the how much food we need to produce, how much land needs to be used, how many resources we really need to feed everybody on the planet, and whether or not we can, considering topsoil is being decimated, our water supplies are, aquifers are being, sucked dry. Yeah, and we've gone past it. According to the estimates, we're just blowing past that, and like, come on, I'm just gonna. We can't just sit here and eat popcorn and watch it anymore, you guys. We all need to start making some changes. And change isn't fun, but maybe we can make it that way.
Those limits, they're there because we do things a certain way. If we start rotating crops, eat less meat, are smarter with our water, we can accommodate more people, which, like it or not, there's a lot of us and we all need stuff.
Yeah. Noodles in the chat room is saying, I eat meat. Love it. So yes, I eat chicken, which is a kind of meat. But when we're talking about meat, it's really red meat and its impacts that we talk about. And at this point in time, I'm not saying don't eat meat.
Yeah.
Eat less of it.
Less
and
meat.
We've gotten it in the United States, at least. It's like meat, red meat every meal. It's like, who needs tri-tip 5 days a week? Who needs, mix your diet up and really make that steak something to appreciate. Maybe don't have a hamburger every day because, I mean, that's not going to be good for you anyway.
It's true.
Just maybe eat your meat, but eat less of it. Yeah. That's all I'm saying. That's all I'm saying.
Word.
But as I'm saying this, you guys want to talk about surfing?
Yeah, of course.
Yeah. This is some interesting physics news that I'm sure Anil
Yeah. Is this
is
water
paying
surfing?
attention to. This is
Or is this internet surfing?
This is neither. This is energy surfing,
Oh,
man.
what?
There is an experiment at CERN called the Awake experiment, otherwise known as Advanced Wake Field Experiment, in which basically like surfers surf on the wake of a jet ski or something, or you I've seen videos of people who have they're holding onto their thing and they're on their board surfing on top of the wake, and it's just like pushing them forward, and they're keeping up and they're going, and it kind of the wake accelerates you forward in a sense. That's what they're doing. They're using this basic principle of one wake to accelerate something else in their study of very small particles. And potentially this experiment, which was, I guess they first started talking about it, not long ago, and they approved the project in 2013. And so they've just been getting it going, really. And so this is a really important first step toward realizing the vision of smaller and stronger particle accelerators. Particle accelerators are necessary because we want to smash the particles of matter together to see what makes them up. And the faster we can get those particles going, the littler, tinier bits we can create, right? So we can see more about, the little particles that break apart when the Higgs boson is smashed, right? What little particles come out? Another news this week, the bottom quarks. 2 bottom quarks. Woo, bottom quarks. Verification of standard model. Woohoo, we got more standard model verification at CERN as well. But in this experiment, they're taking these they're taking the idea of these big particle accelerators, and they're saying we can make it smaller. Let's try and make it a little bit smaller, a little bit maybe less energy put in, and faster, bigger, little tiny particles. And so this is a proof of concept. They were able to accelerate electrons by a factor of about 100 over a length of just 10 meters. And the linear accelerator at Stanford University is like a mile long. So instead of a mile, we're talking 10 meters. This is, a high dive, right? This is small area particle acceleration.
So imagine if you made that a mile long.
Right? Yeah.
Goes so fast.
Go so fast. And so they took electrons and they were externally injected into the wake accelerator at an energy of around 19 million electron volts. And then with the wake field, the wake that they surfed on, those electrons were accelerated to an energy of about 2 giga electron volts. So this is a massive amount of acceleration in a very short space. And they are going to keep working on increasing the acceleration power and what they're able to do. But this is pretty exciting news for high energy physics that this idea works. And so when I talk about how the accelerator works, it's basically there's the electron beam, that's one beam that's getting in there. And then there's another beam that's the accelerator, and that it's called the drive beam. And basically it is the wave that the electrons surf on top of. So you have a bunch of particles. I think electrons are lasers for the drive beam, and then usually, but this time in the Awake experiment, they're using protons. So they're using protons to drive the beam, the surfing wake beam of the electrons. Anyway, there's technical stuff in there, little tiny particles, but the general theme of it, the analogy you can come to is that by having this wake, the drive beam that allows the other beam to hitch a ride and basically surf on top of it, it can accelerate the energies that can be attained by those subatomic particles so that we can eventually take one beam of subatomic particles, smash it into another beam of subatomic particles, and then see what comes out.
So scientists make things go fast. Scientists smash.
That's right. Scientists are the Hulk. There we go.
I got it.
We got it. This is exciting news out of CERN, and exciting news from New Horizons, our wonderful mission that went out to Pluto and took images of Pluto in ways that we have never seen that dwarf planet before, or its moons. It's still heading out to the Kuiper Belt. It is going, and it has taken the very first image of Ultima Thule.
What's that?
That's next. It's the target. Ultima Thule is the target where New Horizons is heading. And it's, you know, when you look at it, you're like, what is that? It looks like a white pixel in a gray screen. It doesn't look like much. And really, yeah, it is a couple of white pixels in a fairly dark field screen. But what it is a target lock. And New Horizons has its next, the place it's going to go be a tourist next in its sights. And it has taken this picture of this very distant object.
Do they have any idea how far?
Right now, the object is about as far from New Horizons as the Earth is from the sun.
Okay.
And we know that New Horizons is way out past Pluto at this point in time, some 6 billion kilometers out there, something like that. It's pretty far out at this point in time. It has about 160 million kilometers to go, but where it is this is, you know, if you want something for your bar trivia, this is the most distant picture ever taken from Earth. Nice. The Voyager craft used to hold that record, but now New Horizons is the farthest craft to have snapped a picture.
Apologies
vacation.
if we talked about this already, but has New Horizons left our solar system at this point?
No. New Horizons is still well within our solar system.
Is Ultima Thule in our solar system?
Yes, it is within our solar system in a group of objects, distant objects called the Kuiper Belt objects. Yeah. And it's the Kuiper Belt is where frozen. It's very cold, and it is really left over from when the solar system formed. So this is we are visiting something that has been around since, probably without changing very much, since the beginning of our solar system. That's where we're headed. We're going to go out, you know, it's like going out into the old neighborhood to see what's happening in, you know, what does the old architecture look like?
Yeah.
Before all the newfangled architects came in and changed things up.
Oh my goodness.
What did it look like? Yeah.
Nice.
Yeah. Some fun news there. Blair.
Yes.
Do you have some stories for me? Should we go directly into the animal corner, maybe?
Let's. Yeah.
Yes, it is time for Blair's Animal Corner with Blair.
She loves our creatures, great and small. Biped, millipede, no pet at all. If you want to hear about animals, she's your girl. Except for giant pandas and squirrels. There's Animal Corner.
Kiki, I have some really exciting cleaner shrimp news. I know you've been waiting for it.
Wait, you mean you got me a house cleaner? Someone's gonna
No.
come clean my house?
No, but if
Darn.
you have any injured fish, some cleaner shrimp might be able to help you out. We've talked in the past on the show about cleaner shrimp and how they have these cleaning stations, and the shrimp and the fish have to somehow communicate. The shrimp has to signal, hey, come over here, I'll clean you. And the fish has to signal, hey, I'm going to come over and get cleaned, but I promise I won't eat you. And so this is very complicated already, but this new study from James Cook University wanted to see how well these cleaner shrimps were, how good they were at cleaning parasites off of fish, because a huge amount of pesticides and hormones and things that are pumped into farmed fish are there to prevent parasites. So in Southeast Asia, for example, where there are cleaner shrimp that take care of fish, between 30 to 50% of farmed fish there are lost to parasites. Sometimes people lose half of their take to parasites. So it would behoove them to pump their fish farms full of things that would help prevent that. The problem is, as we know, one of the biggest problems with farmed fish is when you pump chemicals or hormones or antibacterials or whatever they are into a fish farm, it goes into the water table, it leaches out, it causes further problems. So how can we find a greener alternative? Well, they wanted to see if cleaner shrimp were up to the job. They wanted to see how this kind of relationship worked, because occasionally fish do eat shrimp, and occasionally the shrimp will eat mucus off of the fish, which hurts them. So they used high definition cameras to record the details of interactions between cleaner shrimp and fish. And they found that the shrimp did not aggravate existing injuries when they were there. This is just kind of a thing that they discovered. And they also found that they didn't further injure the fish. They kind of anticipated that if the fish had an open sore somewhere on their body, they might actually feed off of the open sore. Further analyses of these images showed that the cleaner shrimp were reducing redness of injuries. This is good because injuries in fish are susceptible to invasion by other pathogens like viruses and bacteria, because they're just floating in water. It's all right there. So the reduction of redness in shrimp, they found, actually indicated that the cleaner shrimp were reducing infection. So this is a whole extra side of this, not just, hey, you can remove these parasites, but also you can heal the fish.
So how does that work? I mean, I would imagine if you're getting rid of kind of dirty stuff on the outside of a wound, then maybe it would be, as if somebody came along and washed it or cleaned it. But, you also have your cells and everything coming up from the inside of the body, trying to fix the skin. And, maybe you'd think the cleaner shrimp could potentially get in the way of that as well.
Yeah, it's a good question. One thing that they do mention is that cleaner shrimp are known to indirectly influence the health of fish by reducing stress as a function of cleaning. So it is possible that this is just like going to the masseuse or to the spa. It takes the stress away. Healing becomes easier. The path to healing is easier. So it's possible that the act of being cleaned is just making them more equipped to bounce back from an injury. But it does seem pretty immediate that they clean the wound site and it is less red.
Interesting. Yeah, Growly Bear says the same way they use maggots to eat dead flesh to promote healing.
Oh, yes. Yes, that
there
old
is
thing.
that.
Yes. Actually, I'm also wondering if, you think about swelling and redness in injury. What do you do if you do that? Besides washing it, you often put ice on it. I'm just wondering if the act of cleaning is cooling the area down because they're pushing water across it. I I don't know. There's lots of elements to what would be considered cleaning that might have some weird ulterior function. So that's next for sure. They're not sure what the mechanism is, but this does have a very important application because it could help fish farms raise fish more sustainably. So
add some shrimp to your fish farm, and your fish will be healthier, happier, healthier.
Yeah.
Awesome.
So another story I wanted to bring up before I talk about poop, because the poop story is very fun. But first I wanted to talk about a really important lasting finding that happened in evolution and the evolution of vertebrates, which does not happen often. I feel like it happens sometimes. We talk about dinosaurs a lot, but current vertebrates on our planet, we usually have a pretty good idea about where they go in the tree of life. But there's one group that has always been the weirdo, and we don't know where it belongs, and it's turtles. And there was something that came up this week that might have finally solved this question of where do turtles belong?
Turtles belong on the side of a creek.
True, or a log, perhaps. Yeah. So when I was in college, I've told this story on the show before, but when I was in college, they had this kind of dotted line in evolutionary history where there were no turtles and then there were turtles. And in the class where we were talking about that, there was breaking scientific news in the couple of weeks that we were talking about it, where they found this new fossil that had a plastron, the bottom part of a shell, but not a carapace, the top part. So they found this thing before, and it was this almost missing link, but there's still parts missing. They still weren't sure where the beak came out, and they weren't sure when the carapace showed up. They weren't sure what happened to the ribs in between this plastron and no plastron. So there's still lots of questions, and they still couldn't figure out if they belonged in anapsids or diapsids. Anapsids being the older kind of ancient reptiles, and diapsids, which are snakes and lizards. So they're this dotted line. Well, this week, a new fossil was discovered, 228 million years old, and it is answering a bunch of questions. This turtle is over 6 feet long. It has this turtle-shaped body, but it doesn't have a shell. It's disc-like. It has a long tail, and it has a beak, which, remember I said the turtle ancestor that had a plastron but no carapace did not have a beak. So this guy, Aorhynchocheilus sinensis, that's the one I messed up on, of course. So
good work there.
Aorhynchocheilus is dawn-beaked turtle. Sinensis means from China. These guys have this beak, but no shell. And so this tells evolutionary biologists that turtles are most likely the result of mosaic evolution. So traits can evolve independently from each other at a different rate. Not every ancestral species has the same combination. And so knowing that modern turtles have both shells and beaks, and we've identified both of these fossils as being ancestors of turtles, it's looking like mosaic evolution, which is crazy, not what we anticipated. But the thing that I got really excited about was kind of a footnote in it all, which is that they looked at the skull and they found out they're diapsids. They have 2 holes on the sides of their heads, which means they're more closely related to snakes and lizards. So that dotted line in every cladogram ever of vertebrates may now turn into a solid line.
May, because there's still, like, wouldn't genetics just tell you? Like, couldn't you just look at genetics? I mean, this is doing phenotypic cladistic.
The anapsid diapsid thing has been, to this point, fairly foolproof. That has been really this very clear line that has not yet steered anyone wrong. But I agree. I think that DNA is the only way to figure out exactly where that solid line connects in, because now we know, okay, it belongs further over here than over there, but we don't know where. So that's really the question, is where is this common ancestor? So now we're looking for, it narrows down the search. We are now looking for a common ancestor between snakes and lizards and turtles. Did they all break off kind of at the same time? Did turtles break off earlier? We don't know. But we know that they're more closely related to them than other reptiles. So
interesting.
and
of
course,
the
researcher says this is
What?
cemented, the debate is over, which of course it never is in science, but anyway.
It's cemented. Who says that in science?
Oh
They're very proud of their results.
Very proud.
And they should be. This is a big step for turtle science, but
Yes.
but the I think it's fascinating. This is something that we haven't really talked about much, this idea of mosaic evolution, where we kind of think of everything as a straight line where, but we do know that occasionally traits get lost. But when they're lost, are they really lost, or are they just not expressed? So there's this idea in evolution, we have this, okay, there's natural selection, right? But natural selection only acts on the traits that are really being expressed.
Right.
The things that are involved in reproduction and heredity and the ability to survive, those things that are expressed. But there's a lot of other stuff that's there in the genome not being expressed.
Yeah.
Or maybe not, maybe there's a little mutation in there, but it's still wound up in a histone and it's hiding somewhere because of the epigenome. It's not being turned into something yet. So it doesn't have a beak. They don't have, they don't have this shell yet, whatever. One part evolves in one group, another part evolves in another group. They all maybe have the genes that are in there, and they're slowly combining the traits. Expressions are there, expressions are lost, and suddenly, boom, a turtle appears.
And just kills the game. Just does so well. They've just been here forever.
Right? Well,
turtles are just perfect at what they do.
Being turtles.
Being turtles. Right. Kiki, before we exit the corner, do you want to talk about poop?
Yes. Animal poop, I hope.
Specifically, naked mole rat poop. More specifically, naked mole rat queen poop.
This is very specific.
Yes.
This is very specific. Yes.
This is a study from a bunch of institutions in Japan working together, collaborating on this, looking at the very unusual eusocial structure of naked mole rats and knowing that there is a single reproducing female called a queen. There are female subordinates that care for them, knowing that these subordinates have underdeveloped ovaries, cannot reproduce, have no hormones associated with maternal care. How?
They're kind of like bees, right?
Yes, but how do they become nurses to the queen's babies? How does that happen? If there's no hormones that would drive that behavior, how is this happening? In comes the poop. So they noted, looking at naked mole rats, that they eat their own feces. They wanted to see if the naked mole rats closest to the queen might be eating her feces as well. So what they did is they fed groups of different captive female worker mole rats different kinds of pellets. Some got pellets with fecal material from a pregnant queen. Others got the same from a queen that was not pregnant. Some got pellets with no fecal material from the queen, the lucky ones. And others got pellets that had been enhanced with the hormone estradiol, which is
estradiol.
Yes, which is naturally produced by the queen. So,
and is found in many birth control pills.
Yes. They found that the ones who got fecal material from pregnant queens and the added estradiol were more attentive to offspring. So it would follow, they're pretty sure here, that they are getting these hormone cues from eating queen poop. My favorite part about this story by far is that they noted in a naked mole rat colony that just a few subordinate females spend time with the queen, which means a huge amount of subordinate females that care for babies are never around queen poop, which means there is most likely a trickle down of estradiol from the queen's poop to the female subordinates that hang out with her, that eat it. Then there's residual amounts in their poop that then another naked mole rat eats. There's residual amounts in their poop. So there's this cascade, there's this trickle down of hormones that are creating this maternal behavior.
Wow, the trickle down theory of naked mole rat poop.
There we go. You're welcome, everyone. Kai liked that one, I could tell. There we go. That's what I got for you.
Oh, wow. Yeah, it's so interesting though that for, there are many animals in which, because of the way their digestive system works, that feces, the poo is healthy. It is something that needs to be consumed. And, we are animals in which that is not the case, but there are others in which it is. And so it's good to understand how it works and how it might actually have this kind of interesting hormonal effect, which is actually a signaling cascade that signals and induces behaviors.
Absolutely. Yeah. And so mole rats, as predominantly herbivores, they eat things that are not as easy to digest as the plants that we have so carefully genetically engineered and bred to be super digestible. They're eating things that are much harder to digest. It comes out often with a lot of nutrients still left there. And if you're a naked mole rat, you already have no shame. So you might as well get the nutrients out of the poop. You already have it. So there you go. Yeah, that's why horses eat their own poop. That's why rabbits eat their own poop. There's nutrients there. Don't waste it. You can't waste in nature.
Yeah, I mean the very specific eusocial setup that the mole rats in this situation have does, imply that maybe that this was a good place for them to look. But I wonder how many other animal species in which the eating their own feces, in which this is a similar case, where it's actually a communication channel or a behavioral control channel.
Right. Well, we know that there's a lot of hormone signaling going on through the excretory system and a lot of animals. We think about animals that the males will taste the female's urine to see if she is ready to get pregnant. And we have, the dog's fascination with poop and where other dogs have peed. That's a huge amount of that is testing hormones.
Yeah.
So it's
amazing. Yeah. Well, thank you for adding that top note onto the animal corner.
There you go.
Yeah, I'm gonna move us into some secret tunnels.
Secret tunnels, like the ones under the Denver airport.
No, like in your head.
Uh-oh. Who put them there?
I don't know, but there are tunnels, little tiny channels in your skull that researchers just found out about. So Justin has brought us stories about this, new lymphatic system being connected to the brain, and there was other story about a communication system of that might be important to the development of diseases like Alzheimer's. And now a new study has come out of Harvard Medical School and Massachusetts General Hospital, funded by the NIH researchers, trying to figure out how immune cells get into the brain. So there are some immune cells like in the brain that are part of the brain's response to damage and disease. But these researchers, we know that there are other immune cells that are produced by the bone marrow itself that get into the brain. And so you've got all bones throughout your body. Where do those immune cells come from? Do they come from the thigh bone, your femur? Do they come from the bone marrow in your skull? Does it matter where they come from? We never knew this before. And so the researchers did a bunch of imaging studies and staining to actually target these neutrophils, immune cells that get released from the bone marrow. They found that immune cells primarily come from really close to the brain if the brain is damaged. Kind of makes sense. They found more. They do come from, say, your tibia or your fibula, but the majority of the immune cells that head toward damage in the brain are from your skull itself. Now, how do they get there? They found that there are very specific tiny channels in the bone marrow leading out of the skull into the dura mater, into the meninges of the brain themselves, the lining of the brain, to actually funnel immune cells to the brain. Normally, some of these pathways are used by blood cells to leave the brain, but in these cases, they actually watched neutrophils creeping down the channels, creeping into the brain. Wow. Yeah, and they found, in addition to this, not just this, as if it's not enough, they found a signaling molecule that's called the stromal cell-derived factor 1, SDF1, that keeps immune cells in the bone marrow. And they found that in the brain, or in the skull bone marrow, they found that it decreased 6 hours after a stroke, but it did not decrease to the same extent in the tibia. So when they looked at these different bones in the body, this localized response was very molecularly triggered. Yeah.
That makes sense. Cut down on the extra work.
I mean, yeah, and you can imagine, I mean, your body can mobilize these immune cells from all over, but don't you want the local fire department to come when
Yes.
there's a fire and not the one that's all the way across town dealing with crosstown traffic?
Yeah, especially when you're talking about the grid, the electrical grid for the whole city. You want the local fire department there as fast as you can. That brain's super important.
Yeah,
Take care of me.
you don't want just the local fire department. I mean, this is like, at the airport fire department.
Yes, exactly.
It's the one that knows how to deal with the jet fuel fires.
Mm-hmm. Yep.
Yes. Yeah. So that was a fun little study. You got some microbes for me?
Yes. Well, living in the land of fog, as you and I both do,
That's right.
I was interested to find that fog is an excellent vector for microbes. Fog can transfer them long distances and introduce them into new environments.
What? I mean, I knew aerosolized particles. We know that dust particles from the Sahara travel across the Atlantic. Fog. Microbes.
Yes.
Wow.
Researchers tracked fungal and bacterial communities in fog delivered to 2 fog-dominated sites, Maine and Namibia. And they looked at samples of fog, clean air, and rain. They wanted to see the variety and abundance of microorganisms present at both sites. Bacterial and fungal DNA was extracted from filters. They looked at trends within and between sites and analyzed them. They found fog droplets were found to be an effective medium for microbial sustenance and transport.
Wow, sustenance.
Yes, so it's not, they're not just carrying them, they're growing them. At both sites, microbial diversity was higher during and after foggy conditions when compared to clear ones. And they found that marine influences on fog communities were greatest near coast, but still evident 15 kilometers inland. They found both soil and ocean sources of microbes in those places.
That's fascinating.
Yes. So the twist here that's especially weird is not just that they're carrying microbes, but on the journey, they not only survive, they change, they grow, they evolve. The fog itself is a novel living ecosystem. Fog at both sites contained pathogenic microbes, including suspected plant pathogens and species known to cause respiratory infections in immunocompromised humans, which raises concern about the role of fog that could play in transporting harmful microbes. This is just the beginning, of course. Hopefully, this will bring more studies up to the forefront where they can better understand the role of fog as a vector, and in particular, warming sea surface temperatures. Because as the planet gets as the planet gets hotter, warming sea surface temperatures, which will then alter wind, are all going to affect fog distribution, what microbes are picked up, and how far the fog goes as well. So there are certain areas, Kiki, you and I might be pretty well used to the fog ecosystem.
Right.
But people 100 miles inland might not. And so a change in our planet that could push fog further inland could bring new pathogens to these new communities of plants too.
Yeah. Another interesting side to it, though, is there are certain bacterial diseases that are prevalent in drier areas, and when people go to foggy areas, they say it's just the moist air that helps, but maybe it is something about the microbes that are being inhaled and are part of that.
Mm-hmm. Yeah, absolutely.
Yeah.
I never thought about fog being its own
Ecosystem.
ecosystem.
Right? No.
Yikes.
And
it's
there's
really
also
going to change my relationship with the fog, I have to say. I love the fog. And now,
in San Francisco, the fog is named Carl.
yes.
And so you say, hey, Carl. Now it has a new meaning, right?
Yeah, I'm really talking to somebody.
You are really talking to multiple organisms, and you say, "Hey, Carl, don't give me that virus, all right? Hey, Carl,
Carl,
don't pass
be
along that
cool,
pneumonia bug.
Carl.
Be
No
cool,
thanks,
Carl."
I'm feeling immunocompromised today. Chill, Carl.
Well, something that's really cool is a prototype bionic eye that has been 3D printed by researchers at the University of Minnesota. This is the first time that a fully 3D printed array of light receptors has been created on a hemispherical surface that's rounded like an eye. And so they're really saying this is like going toward a bionic eye type situation. I love a quote. This is published in Advanced Materials, which is a peer-reviewed journal about materials science. And one of the authors, talking about what they're doing. I mean, he's like, we have a long way to go routinely print active electronics reliably, but our 3D printed semiconductors are now starting to show that they could potentially rival the efficiency of semiconducting devices fabricated in microfabrication facilities. Plus, we can easily print a semiconducting device on a curved surface, and they can't.
Okay.
That's like the scientist's version of nah 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 nah. Like,
Really?
I've got this and you don't. Yeah, so they're able to print this semiconducting material on a curved surface, which is not an easy thing to do, in a way that it is still able to actually receive and conduct light. It's quick and can potentially, and one of the researcher, Michael McAlpine, he says that one of the reasons he's really working on this, they've already 3D printed a bionic ear and several other replacement human body parts, but this one was really inspired because his own mother was needing a new eye, and it's like, when are you going to help me out with that?
Yeah, really good question.
Right?
Like, stop messing around with those ears. Give me an eye.
Give me an eye. Yeah, it's amazing the resolution that we've gotten to now, the ability to 3D print these semiconducting materials on a surface in a way that is light sensing and could be used to take electrical signals from the light, the photo detectors, and have them be used as a potential bionic eye.
Hmm.
Right? Need a new
Yeah.
eye? Just print it.
Yeah, that's really exciting. This is many, many, many steps away from a bionic eye, it would seem, right? I mean,
It is many steps away from a bionic eye.
just in small part, figuring out how to make it talk to your brain, right?
There is that. Yes. I mean,
Making images is the most complicated thing.
but it's really the brain makes most of the images. Our eye is just a simple light detector when it comes
Right.
down to it. So, you
But
know,
how do you make that talk to that and make
right.
it all go right?
Their researchers are working on it, but
I'm excited.
one of the things is how do you print something that would be hemispheric and would detect light in the same way that our own eye does? And then you have to get the structure right first to be able to hit the functionality.
Yeah. That is very cool. I mean, I'm sure there's lots of applications for 3D printed curved electrical surfaces. That's neat.
Yeah. So right now, this is maybe something that could be used on a robot because it's a hard surface, and so they have to move forward also to a soft surface like our squishy water-filled eyeballs. All right, tell me another story.
Oh my God, I just can't even. Do you ever feel like teenagers are hard to read? I definitely do. I work with teens and sometimes I just don't even know what they're talking about.
Well, sometimes I don't think they know what they're talking about. You know, they talk
Yeah.
to each other and then they get in fights for weird reasons, and you're like, "Why are you fighting? There's
This is
no reason."
exactly what I am here to talk to you about. This is a new study from the Journal of Nonverbal Behavior looking at the ability for teens to understand what someone is feeling based on their tone of voice. This finding found that while adults are able to accurately read a range of emotions in the voices of adults and teens, teens are able to read the emotions of adults fairly well, but teens are far less able to understand what their peers are talking about. This is
Mm.
particular attention to tones of voice which express anger, meanness, disgust, or happiness. They took 140 recordings made by child and adult actors. They played them to 50 teens between 13 to 15 years old and 86 adults between 18 and 30. The recordings were of neutral phrases like, "I can't believe you just did that," which could be expressed with different intonations, meaning different
Yeah,
things.
yeah.
Participants were asked to select the emotion based on the recording, and they showed a clear divide where it looks like it might be twofold. One, teens are less able than adults to produce recognizable emotions with their voices, and adults are just kind of good at the subtlety, finding the subtlety. But that two, they don't have as good of understanding of the expressions of others. So adults were very straightforward with our emotions. We figured out how to emote like a human. And so they can read us just fine, but their developing skills are not yet able to read the developing verbal skills of their peers.
That's fascinating. So adults know what the teens are saying all the time. It's
Mhm.
just like, "Okay, I know you're in this mood. I got you. We'll
Yeah.
figure it out." But it's kind of like the juvenile birds who still haven't quite figured out they haven't crystallized their song yet.
Yes, exactly. So this, aside from
Yeah.
being funny and very indicative of teens in a lot of ways, it will help with a lot of communication or social difficulties that teenagers have, knowing that it might be developmentally totally fine for them to be fighting with their peers, not understanding each other. It's not fun. Nobody said the teenage years were particularly fun for the people around the teen, or maybe the teen themselves. But at least there's some scientific foundation here that it's normal and that it's most likely able to improve with time. Just give it time.
Yeah. I wonder if it's probably definitely with time. I mean,
Yes.
although there are some adults who their emotional intelligence is to be desired. But that said, it is interesting. It's probably I'm wondering if it's only I'm gonna go with the hypothesis that it's a combination of not really picking up on the subtleties of things yet, where adults get that, and also not producing things in a clear-cut way. And maybe
Yeah, that's what they suggested for sure.
Yeah.
Which,
Fascinating.
I mean,
Teenagers.
if you think back to teenage years for just a second, it's not surprising that they can't emote a clear emotion because they're probably not having clear emotions.
Absolutely.
I remember being a teenager and my mom coming into my room being like, "Why are you crying?" And me just going, "I don't know."
You're not alone.
Yeah, it's teenage years. Your hormones are just crazy and you're trying to figure out how to be an adult human and you can't. It's okay.
It's okay.
Okay.
And you know what? For all the teenagers that may be listening right now, we're not bashing on you.
No!
We're just letting you know it's going to get better.
Yeah, we're just letting you know being a teen could be the pits and there's science here to prove it. So
it's
hang on.
It's a confusing time.
Yeah,
just
and we get you. We get you. We're giving you space. We're waiting for you over here.
We are waiting. We're here and we see you. We hear you. We understand you, even though you don't think we do. All right. What else is going on? I have two very, very quick stories. Some really interesting, weird news about addiction in bees. It turns out that social, like bees who have been exposed to neonicotinoid pesticides are more likely to show a preference for neonicotinoid-laced food later. So neonicotinoid exposure, this pesticide exposure, leads to them actually wanting to have more of it and to expose themselves more.
That's not good. Bees, no.
Yeah, which you can imagine how that would have this kind of feedback effect of increasing pesticide exposure and having negative effects on the colonies and all that kind of stuff. So, yeah.
Buddies, leave the pesticide alone.
Yeah, the researchers say our results highlight the need to incorporate attractiveness of pesticides to foraging bees and potentially other insect pollinators, in addition to simply considering the proportion of pesticide-contaminated floral resources within the foraging landscape. Bees, don't get them addicted. And then finally, we've talked a lot over the many years about Japan's Hayabusa mission to asteroid Itokawa. It was the first asteroid sample return mission. It ended in the demise of Hayabusa. Hayabusa crashed and burned, but the heat shield stayed intact when it landed, and they did actually bring back some dust grains from the surface of asteroid Itokawa. And these phosphates dust grains have been analyzed by researchers, and the researchers now have finally published in scientific reports pinning down the origins of asteroid Itokawa. They say that this little pile of dusty rubble, which is really not a rock so much as a bunch of little pieces of rock stuck together through attractive forces. It formed about 4.6 billion years ago, around the start of the solar system, but about 1.5 billion years ago, apparently, it had a car crash with another asteroid. And Itokawa was nearly obliterated, but the remains are what we see today, and the collision is probably what kicked it into the trajectory that kind of put it on its path to become captured by Earth's gravitational forces and to become one of Earth's near Earth asteroid objects to be studied. So there is a question about this. Maybe Itokawa might run into Earth in about 1 million years. So we want to study these near Earth objects and find out what we're looking at. But Itokawa, it came from somewhere in the beginnings of our solar system.
Wow. Nice.
Yeah. Yeah. So, and also one of the interesting things is that because of the type of asteroid it is, it's in a from where it is, it's in a different kind of asteroid family. And so, there is some information about it being the asteroid family it actually originating from being different than what you would expect, probably because of this collision that it had.
So an asteroid is out in space and a meteorite hits Earth, right? That's the main difference?
Yes.
So
an asteroid can become a meteor.
Yes.
A meteorite.
Yes. So this is an asteroid on Earth, which is kind of an oxymoron.
It's little parts of the asteroid on Earth. That's right.
Yeah.
Yes. It never went through that whole meteor phase.
My goodness,
Really.
that's pretty cool.
It is kind of cool. And Japan has launched Hayabusa 2, and they are planning a second asteroid return mission to asteroid Ryugu. It's going to spend 1.5 years surveying the 0.5 mile wide asteroid and bringing back some bits and pieces of it so we can find out more stuff about these near Earth objects. More cool stuff happening. Science never sleeps. It is not cemented.
I know. I was like, that's the most unscientific thing you could say, dude. For real? That's going to be your quote? Wow. Okay.
You could say, well, it's not a dotted line anymore. We've got some solid evidence. Yeah.
Yeah, that'd be fine.
It could be fine. It could be. So, are we at the end of our show?
We did it.
We did it, you guys. We made it to the end of another show. And it's time for all of the thank yous. Thank you all for watching us. Thank you to Fada for helping out in the chat room, Gord for helping out in the chat room, Fada for helping out on our social media, and for helping with show notes every week. Identity 4 for recording the show. And I would like to say thank you to all of our Patreon sponsors. Thank you to Richard Onomus, G. Burton Lattimore, Paul Disney, John Ratnaswamy, Craig Landon, Tony Steele, Alex Wilson, Steve DeBell, Andy Groh, Joshua Fury, Charlene Henry, Harrison Prather, Ken Hayes, and Ed Dyer, Mark Mazzaros, Jack Matthew Litwin, Jason Roberts, Bill K., Bob Calder, Time Jumper 319, Kyle Washington, Eric Knapp, Richard, Brian Condren, Aiden Jeff, Richard Porter, Jacqueline Boyster, Noodles, Kevin Reardon, David Neighbor, Christoph Zucknerek, Noah Zemke, Jim Seabright, Ashish Pants, Ulysses Adkins, Sarah Chavez, Artyom, Rick Ramus, Paul, John McKee, Jason Olds, Brian Carrington, Christopher Drya, Lisa Slazewski, Jim Drapeau, Greg Riley, Sean Lamb, Ben Rothig, Steve Lefseman, Kurt Larson, Rudy Garcia, Marjorie, Gary S., Robert, Greg Briggs, Brendan Minish, Christopher Rappin, Flying Out, Eric Luthen, Matt Sutter, Mark Hessenflow, Kevin Parachan, Byron Lee, EO, Mark, Tyrone Fong, and Keith Corsell. Thank you so much for your support on Patreon. If any of you are interested in supporting us, you can find information at patreon.com/thisweekinscience. Remember that you can also help us out simply by telling your friends about TWIS. And on next week's show, we will be back once again. It'll be September, and we're going to be here on Wednesday, 8 p.m. Pacific time at twis.org/live, where you can watch and join our chat room. You can also watch and join our chat room at our YouTube channel. Don't worry if you can't make it, though. Past episodes will be there archived at twis.org and on our YouTube channel.
Thank you so much for listening and enjoying the show tonight. TWIS is also available as a podcast, just for your ears. Just search for This Week in Science in iTunes, or if you have any kind of mobile device, you can look for TWIS for Droid in the Android marketplace, or This Week in Science in all of the Apple things.
That's right. And for more information on anything you've heard here today, show notes will be available on our website, twis.org, with links to the stories and all that kind of stuff. You can make comments there too and start conversations with the hosts and other listeners.
Or you can contact us directly. You can email Kirsten at thisweekinscience.com, Justin at twisminion@gmail.com, or Blair at blairbaz@twis.org. Just put TWIS, TWIS, in the subject line so your email won't be spam filtered into oblivion. You can also hit us up on Twitter, where we are at TWIS Science with one S, at Dr. Kiki, at Jacksonfly, at Blair's Menagerie. We love all of your feedback. If there's a topic you would like us to cover or address, something you want us to put in the Zazzle store, or a suggestion for an interview, please let us know.
And we'll be back again next week. We hope you'll join us once again for more great science news.
And if you've learned anything from the show, remember,
it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. This week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 I've got one disclaimer and it shouldn't be news. That what I say may not represent your views, but I've done the calculations and I've got a plan. If you listen to the science, you may just get understand that we're not trying to threaten your philosophy. We're just trying to save the world from jeopardy. And This Week in Science is coming your way. So everybody listen to everything we say. And if you use our method instead of rolling a die, we may rid the world of toxoplasma gondii. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 I've got a laundry list of items I want to address. From stopping global hunger to dredging Loch Ness. I'm trying to promote more rational thought, and I'll try to answer any question you've got. But how can I ever see the changes I seek when I can only set up shop 1 hour a week? This Week in Science is coming your way. You better just listen to what we say, and if you learned anything from the words that we said, then please just remember it's all in your head. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. 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 This Week in 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 science.
We made it. I think Kiki's tending to her menagerie again, but in the meantime, I can tell you all what I did right before this. I talked for 45 minutes before TWIS tonight. I was at Skyline College and I was asked to do a fun talk about my career in science. So I dusted off the talk that I did at Taste of Science in April, and I did that for a room full of undergrads who are not sure if they want to be scientists or not. So that was pretty exciting. Talked about my time working at the zoo, talked a lot about TWIS. It's really good. Yeah. Yeah, it was pretty good. Also, I just tweeted at Carl the Fog. I hope I hope he sees it. I tweeted at him that he's gross. I learned that he's gross.
What would you say is gross?
Carl the Fog.
Carl the Fog, you're gross. You told
So I
him.
tweeted at him. I wrote, "Ew, at Carl the Fog. Turns out you're crawling with microbes." And I sent him the. We'll see
Perfect. That's right. See if Carl writes back.
See if Carl responds. Yeah.
So how was your talk today?
It was great. It was really cool. It was
Quiet.
it was the first in a series for the whole semester. So I knew it being the first one, there was probably going to be less people there, but the classroom was about half full. I mean, it was a after hours lecture about non-traditional careers in science. And so they have these people coming every other week for the whole semester. And so I kicked it off and I did pretty much the exact same talk that I did at Taste of Science in April. I tailored it a little bit more to the group, but it was good. It went really well. So it was interesting. Their questions were very they were much more probing than the questions I got at Taste of Science, probably because, at Taste of Science, they serve alcohol. So I don't know if that changes the type of question where it's just like, what's the most crazy thing you've ever worked with at the zoo, were questions I was getting before, but they were asking lots of like very poignant.
These are students too. They want to know what they're
Yes.
do with their lives. They're not just there to be entertained. Yeah.
Yeah. So they wanted to know how you get an interview and how you know science is the right thing. And what if you're not sure what major you should declare? And I keep being told that every decision I make will narrow my pathway for the future. I was like, no, wrong. They tell you that. It's not true. Just try stuff. And if you don't like it, try something else. It's really not that hard. And, somebody, the professor even said like, oh, well, can you explain why you didn't go to grad school?
You?
And I was like, well, there's a couple reasons, but also it's never too late. Like, I don't know. And then
that is the truth, actually. And I'll say that right now. It is never too late to go to grad school. And so if you're doing something professionally that you're doing fine in, and you don't need to go to grad school, then do what you're doing. But if you realize as you're working that you could take a step up and do something more, if you went to grad school and did that research and got that title, then you do it.
Yeah, exactly. And so I kind of just said, oh, well, after college, I was super done with school. I don't regret not going straight into college or into grad school because I would not have valued it because I was so burnt out. I was beyond burnt out academically when I left college, and I wanted to work and I wanted to be doing things with my hands for money right away. I was done. And so I had to leave, and I don't regret that at all. But I also am not going to say with 100% certainty that I won't ever go back to school later in life.
And you shouldn't, because
yeah.
you might.
One
Yeah.
student did ask me, if you weren't doing what you do now, where do you think you would be? I was like, whoa, that's crazy.
Yeah.
But so, yeah, I thought
And
about it
what'd
for
you
a minute.
say?
I said, if I hadn't started volunteering at the zoo,
You'd be fighting squirrels at the Jerusalem Zoo.
yeah.
No.
If I didn't start volunteering at the zoo when I was a kid, and I didn't figure out that this is a career path, and I also didn't get burned out in college, those two things would have to happen, I'd probably be on track to be some sort of professor. I think that's what I would do, because I love working with young adults. I love teaching, and I was a very academically minded person when I was younger. So I do feel like
I like imagining you in playing saxophone in a nightclub.
yeah. Yeah. Yeah, like Parks and Rec, what's Ron Swanson's alternate
Yeah.
identity? Oh
Yeah.
my god.
No,
Yeah.
I kind of see you, in a nightclub.
Yeah, absolutely.
Lisa Simpsoning it up.
Uh-huh. Oh my gosh. Yeah. So yeah, it was really great. I had a great time. And I was like, okay, I'll start talking at 4:30 if you can promise that I'm leaving by 5:30, because they only did these on Wednesdays. I was like, well, I almost said no. I said, I can fit it in. I can fit in some SciComm before my SciComm.
You can do it.
I can do it.
Yeah. Yeah. What are people saying in the chat room?
Oh, yeah.
Robert Bigelow said he didn't get his first undergraduate degree until 40.
Mm-hmm.
Right? It's never too late. Yeah.
Yeah. Do a thing until you don't like doing it anymore, and then do another thing.
And then do another thing.
Sometimes they're related and sometimes they aren't. And that's okay.
Yeah. And then he also says, if you've been in school continuously since kindergarten or Montessori, it's easy to see how a young adult can be burned out by school.
Yeah.
I mean, it's years without a break.
Yeah. It's funny because definitely my really, really, really intense high school contributed to the burnout. There's no question there, because I had 8 hours of homework a night and 8 hours of school a day and extracurriculars. And 3 of those classes were college level, and it was 7 subjects a day, and it was too much. And that definitely contributed. But then somebody also asked me, oh, how do you deal with failure? And I said, oh, well, you know what? That is the one thing I definitely learned from that college preparatory high school, is how to prioritize and how to recognize that you're not always going to get 100% on everything. So there were lots of lessons to be learned from that, but yikes. It definitely affected my trajectory, because I was super duper over school by the time I was done with college. But college was easy compared to high school. So that was nice, because I got to focus on the stuff I was really interested in, and I didn't have to worry about studying for grades or studying to pass tests. I just studied the stuff I wanted to know more about, and I did okay on tests because I was practiced at it,
Yeah. That's good, though. That's I mean, that's kind of how, you hope college will be. It's kind of a fun experience of learning more, learning stuff that you're actually interested in, right?
Yeah,
I
absolutely.
don't know. I'm wondering these days, where it just seems like high school students have to do that, have to burn themselves out on, showing that they do extracurriculars, have, over a 4.0 because they're taking college level AP classes, and they're, holding down this full load and maybe doing research on the side, and they work at a dog shelter, and they do, they volunteer, and they do all these things. I mean, it kind of, I get stressed out thinking about it.
Yeah, absolutely. That's
and then you think, oh, well, college is like, how expensive, and the school loans to make that happen. What's it going to be like, when my son is, 18 years old, 10 years from now? How's that going to be? And like,
yeah, it's very easy for me to stand here and say like, when I have kids, of course it's not going to happen. But I want to be like, I'm going to convince them that they don't need perfect grades. I'm going to convince them to try stuff, and commitments are important, but don't keep doing a thing you don't like. And also, I'm going to convince them that they have to go play.
Playing,
and like relax and allow that teen brain to form so they can figure out how to talk to each other. Yikes.
Yeah. Learn how to talk to your friends, kids.
Yeah. Get your nose out of that book and go get into some shenanigans I don't want to hear about. But just be safe, but go get into some shenanigans.
Yeah. Noodle's son is into criminal justice, was burned out from high school, but he will find his time to slow down and find his way. Yeah, has carried a full-time college semester for the last 3 years. Yeah, it's what you do. It's what you do because you got to get through it, right?
It's there's really some merits.
Rides a longboard. That's good meditation. That's good.
Yeah. The really interesting thing about the way people age and grow up in Israel when I was there is because they have this 2 to 4 years of military service, which I am not suggesting that happens. But as a result of that, everybody gets 2 to 4 years off in between high school and college. And so they have this time to grow up, to learn how to be mature. That's when they go off and have their like dorm room-esque realizations because they're off in the military. So they're off bunking away from their parents and getting into shenanigans, all this kind of stuff. And so they get the emotional intelligence, and they mature, and they figure out priorities, and then they come back. And most students, when they come back, they go into college with a career in mind.
Right. They know, they kind of go, I think I know what I want to do.
Yeah. And almost none of them live at college. Almost all of them work while they go to college and live at home during that time so that they have a savings to start with when they enter the job market. And it changes the way it works so much. It's very interesting.
Yeah. Note to self, take a break. Breaks are nice.
Breaks are actually, I would argue, I could find some research, or if there was research done, it would prove that taking breaks is beneficial to your mental and physical health.
For everyone.
In every sense of the word.
In every sense.
We did a story about mental health days, how they're like a real thing, right? Didn't we? I was just thinking about that the other day because I woke up feeling emotionally and mentally not prepared. And I thought about just going, I'm not coming in today. And of course I didn't. I got up, I got ready, I went to work. I felt very sluggish all day, but I got stuff done, came home. And it wasn't until days later that I thought about it again. I was like, well, maybe my brain really just needed a day.
Yeah.
It's a real thing.
Maybe I just needed to reset.
Reset. And you can't always choose when that's going to happen. Sometimes it's going to happen in the middle of the week that your brain needs like a hard restart. But the problem is it's not socially acceptable yet.
Yeah.
You can't call your boss and go, I'm not coming in today. And they say, are you sick?
No.
You're like, no, I just can't.
It depends. There are some companies that are instituting mental health days, and yeah. But yeah, most of the time you just have to go to your work and do your work, no matter how you feel.
Or recognize that that's a form of being under the weather and take it.
Mm-hmm.
And don't be shy about it. And
I need a mental sick day.
Yeah. Yeah. I think it's something that we ignore sometimes, and we shouldn't.
Yeah. Speaking of that, I do need to take my child to bed because we're back
Yeah.
to school now and he
Ooh.
is up way too late
Oh,
and it's going to be
no.
absolutely impossible to get him up for school tomorrow. He didn't go
No.
to sleep like he was supposed to. He fidgeted and fussed and played games, so he's in trouble.
Uh-oh.
Mhm. He didn't do what he said he would do, and so he's in trouble. But it is time for bed because we need to do that.
Yeah, it's bedtime for sure.
Sleep is important for all brains, especially the developing ones. So, I guess we don't have the I'll see you later.
Okay.
Say goodnight, Blair.
Good night, Blair. Say good night, Kiki.
Good night, Kiki.
And we can say good night, minions.
Good
Good
night,
night,
minions. Thank you for watching. We will be back again next week. Looking forward to talking with you again. Thanks for coming. We're stopping the broadcast now. Pew, pew, pew.